Hey guys, just doing a quick video here on buffers to wrap up our week of missed lessons and get ready for a lab that hopefully should be happening in a week and a half. As you can see, buffers are made when you have a weak acid and its conjugate base placed into a solution, and the notation there says that they should be close to equal in concentration. I think by the books, the concentrations have to be within 100-fold of each other. So what that means is that the concentration of the acid can be 100 times that of the conjugate base, or vice versa, and then you'll get more or less a buffer behavior. Now the quality of a buffer is that you're going to have a system that maintains close to constant pH, even when small amounts of strong acid, that is to say hydronium, or strong base, which is hydroxide, are added to the system. Now the key here is that we're talking about small amounts, so that's pretty important. We're talking about drops or milliliters worth of strong acid or strong base, and then our pH is going to hang out close to the same. Keep in mind that nearly constant means an approximate thing, like you're not going to get big shifts in the pH value. So to talk about this, I've got an example of a system which is the acetic acid sodium acetate buffer, and hopefully you can see that the acetic acid would be our weak acid, and then the acetate component is the conjugate weak base. So if you have a weak acid and a conjugate weak base in solution at close to equal concentrations, then you should be okay. So I would argue that what a lot of people have problems with here is trying to figure out how to represent this actually behaving like a buffer, because I think instinctively, if you made an entity list, you would see that your strongest acid is the weak acid, your strongest base is the weak base. But because we're talking about pH, it's actually more appropriate for us to have a look at how the weak acid reacts with water and then I'll have to do my arrows here, so give me a bit for that. And in so doing, it'll create some hydronium, and then the conjugate. So you'll notice that the conjugate actually pops up into the equation naturally, just for the fact that we're doing an acid-base neutralization, or a Bronsted-Lowry neutralization, I guess. Let me get that to fit. Okay, and then I'll put in my arrows for correctness, and then we can see what's going on. Okay, so imagine that you've made a buffer by putting these components into the solution, and this is the system that you've created. Now, if we then want to add a strong acid, arguably what we've done is we've taken this component. Let me see if I can grab a shape. So we've grabbed this component here, and increase its concentration. Now there's a few different ways of considering this. You could do a new entity list, now including the hydronium ion from the strong acid, and deal with it that way. I prefer looking at it as if it's a Le Chatelier problem. Remember that with Le Chatelier's principle, it suggests that if you stress a system by, for example, increasing the concentration of hydronium ion, the system will respond in order to offset that stress. So by increasing the concentration of hydronium, what we are going to do is shift the equilibrium to the products, and see what I can do just to maybe show that. So there will be some of the hydronium used up in that process, and consequently a little bit of the acetate ion, and therefore some acetic acid will be produced. But as I said earlier, as long as the ratio of acetic acid to acetate ion stays within 100-fold, then everything actually works out okay. And that comes back to the fact that this equilibrium, as long as the temperature doesn't change, is governed by an expression. So let's make that expression. I'm sad I didn't do that earlier. But the expression would look like this. Okay, and then we would have the acetic acid on the bottom here. Okay, so the key here is that because the ratio that we've created here is governed by this value Ka, and we could actually just look that up here. That value happens to be 1.8 times 10 to the minus 5. Okay, the system is always going to rebalance itself by, in this case, using up some of that hydronium in order to reestablish a ratio close to that value. And again, because the volume or concentration, I guess chemical amount of hydronium was low, then the stress that is put on the system is such that a little bit of acetate ion would go away, some acetic acid would be produced, and therefore the pH of the system would probably stay pretty much the same. Maybe just to qualify this a little bit, let me take this equation and rearrange it here just real quick, just to illustrate a point. So since pH is, as you know, the negative log of the hydronium ion concentration, what if we took the expression up above and rearranged it to solve for the hydronium? Oh, looks like I didn't kick out all of my notes from before. Okay, so taking the equilibrium expression, let's do a quick rearrangement here. Okay, so what that would mean is I would get Ka, there we go, times the acetic acid concentration, and then that would be over the acetate ion concentration, okay, and as suggested, because these changes are slight, meaning that only a small amount of acid was put in, so according to Le Chatelier, a small amount of acetate ion would have been used up, and then a little bit of acetic acid would be produced from that Le Chatelier shift. Then arguably the ratio between acetate ion and acetic acid really would have gone pretty much unchanged. And since Ka is a constant, then the value of hydronium ion really should also have more or less gone unchanged once the system establishes this new equilibrium. Okay? So one of the ways that we can see that is by looking at a pH curve, which is going to be a topic for another day. So here's the pH curve for acetic acid in this case titrated with sodium hydroxide. But what we can do is look at this region of the curve here, and I'm going to see if I can just highlight that here. Okay, so this region, you'll notice, is referred to as the buffer zone. And kind of between those hashed marks, you'll notice that the pH is relatively flat. Now, what's really important is that it is not completely flat. Okay, so as suggested, that there will be slight changes to the pH, and you'll notice that, you know, within that region, we're changing almost by an entire unit while still maintaining what's referred to as a buffer zone. So that's something just to pay attention to there. Okay, now you'll notice that essentially what we were doing is we were starting somewhere in this region of the buffer zone. Ooh, let me turn off that pen. Okay, so let's say we made a buffer that was kind of in here, that consisted of acetic acid and sodium acetate. And then what we started to do is add acid, which means that we were kind of going down the curve in this direction. Okay, and what would happen is that we would use up a little bit of the acetate ion, we would create a little bit more acetic acid, and change the pH downward slightly. Okay. Now, what this curve is also showing is that if I also started with a buffer, but then I added a small quantity of base, I would end up working up this way. So either way you go, you actually start to get slight changes of pH, but really they stay more or less constant. Now notice, however, either direction you go, if you add enough base or enough acid, the buffer can become overwhelmed, and the consequence is, well, you just destroy your buffer. You'll remove so much acetate or acetic acid that the buffer can't function as a buffer anymore. So as long as you're kind of within that spot, again between the hashed marks, you'll still have a buffer. There are two very common ways to prepare buffers. One is by taking nearly equal concentrations of the buffer components and you put them together. So in the example that we just stated, if you wanted to make a buffer that consisted of acetic acid and sodium acetate, then all that you would do is grab a solution that contained, let's say, 0.1 mole per liter acetic acid, and all you'd have to do is put it together with a similar concentration, again within 100-fold. In this case, let's make them the same just for ease. And then, because you don't just find acetate ions kicking around by themselves, you would want the salt of the substance, mostly being a sodium salt because it has high solubility. Okay, so if you just took those two components, mixed them together to create a solution that had that mixture, everything's great. The other thing you could do is you can half neutralize a solution. So again, with the same example, what you could do is, in this case, you'd have to be a little careful. You'd have to consider both the volume and the concentration of what it is you're dealing with. So if we wanted to make a buffer out of acetic acid, then if we took, let's say, 50 milliliters, there we go, of 0.1 mole per liter acetic acid, so now we have to consider what we would want to add to this to half neutralize it. Now, This half neutralization is going to have to be with either a strong acid or a strong base appropriately. Since the substance we're using is a weak acid, we're going to do a quantitative reaction with a strong base like sodium hydroxide. Now, for ease, let's consider what would happen if the concentration of sodium hydroxide were 0.1 mole per liter. Okay, so if you added 50 milliliters of 0.1 mole per liter sodium hydroxide to the acetic acid in the question, then the whole thing would be neutralized. You would completely convert your acetic acid into acetate ion, and you would not have a buffer. So what we want to do is push that halfway to completion. So we're going to take, let's say, 25 milliliters of a solution of the same concentration, in this case of sodium hydroxide. And the consequence of that is that during this reaction, the acetate ion will still be there because we've only used up half of it. The sodium hydroxide will get completely used up because we've put in a limiting quantity of that. And then the result is you will have produced a bunch of acetate ion that will now be in solution at about the same concentration of the acetic acid. So that's a very common way of doing that, and the one that we're actually going to use in the lab. And then a few different things about buffers. We prepare buffers all the time in labs for use to standardize things or test indicators, do stuff like that. We're going to prepare a buffer in the lab, as I suggested, and very often they can be used to calibrate things that measure pH. So there are some pH meters that we use in the lab, and quite often they will drift away from their true values. So what we do is we prepare a buffer at different pHs and then stick in the pH meter to use as a calibration. Okay, now those aren't particularly exciting. So places where we might need buffers kind of every day include blood. Of course, we have acidic and basic substances that flow through our blood all the time. And the main source of acid is, of course, carbon dioxide getting into the aqueous medium of our blood, which then creates carbonic acid. Oh my gosh. Okay. It turns out that there is bicarbonate ion that also floats around in the blood, so sodium bicarbonate, likely. And you can see that this being a system containing a weak acid with its conjugate base in the solution, then of course as you exhale the carbon dioxide, the system will lower the concentration of H2CO3, but the pH will remain pretty much constant because you of course aren't getting rid of all of the carbonic acid that's in there, and the pH tends to stay just slightly acidic overall. Your cellular fluid also uses buffers, intracellular fluid, so let me just add those there. And then your gastric secretions, so anything kind of going into your intestines. Of course, you have all kinds of acid in your stomach, and that would not feel very good if that stayed that way all the way through your intestines. So I believe there's a phosphate or a hydrogen phosphate buffer that ends up in your gut to help offset the rather strong acid that we have for digestion in our stomachs. So now that we know about buffers, let's do a quick buffer calculation, and then I think that'll be it. So imagine that we have a system like this one, where we're mixing two non-equivalent equivalent concentrations of weak acid and its conjugate base. Now there's a few traps here that I'm just going to point out. Again, the first one being not recognizing these as a conjugate acid-base pair because the sodium ion obscures it. So you have to remember that we have to observe the Arrhenius behavior and get rid of the sodium ion so we can see that there's the dihydrogen phosphate and hydrogen phosphate buffer system. Probably the best way of doing this is to go back to our equation expression ice solve pattern that we've been working on for months now. So let's see how that goes. Following the tip that I suggested before, let me just get down a little bit. Okay. We're going to take the acidic component of this buffer, again justified by the fact that we're looking for the pH, and we're going to react that with water. Again, I'll add the arrows later. Let's make some hydronium. Okay, so that's the equation that I have. Good. I'm going to leave room for an ice table. It's not going to be very useful, but it'll at least help to frame out some of the thought pattern of what's going on. Next up should be an expression. Okay, pop a line in there. Good. And then ideally what we're trying to figure out is what is the concentration of hydronium so we can find the pH. So let's populate our ice table. So since the concentration of the dihydrogen phosphate is directly related to the sodium dihydrogen phosphate, we'll put that here. The concentration of the water doesn't matter. The initial concentration of hydronium we can assume to be 0 because we don't see a source of that by itself apart from whatever is there from water. And I typed that in wrong, didn't I? Let me go back and fix this. Okay. And then ideally what we're looking for is the concentration here at equilibrium. And using the same kind of approximation that we did before, what we're going to do is assume that the concentration of HPO4 gained here and the concentration of H2PO4 lost here is negligible. And of course the way that we do that is that we need to find the K value that's appropriate here. Now this part is a little tough because of course you have two substances in the mixture that technically could be Bronsted-Lowry acids. So the H2PO4 is the one that we're really interested in, but sometimes you might look and say, well, isn't HPO4 also a Bronsted-Lowry acid? What we have to do is look at that in context. So if we look at the equation that we created, which is the substance in the forward reaction that is behaving like the weak acid? Recall also that since we're talking about Ka, it's important that this substance over here be the substance that we're focusing on, the H2PO4, because it is the substance reacting with water. And that, of course, fits the definition of what Ka is all about. So if this is a substance acting like the weak acid, then 6.2 times 10 to the minus 8 is the important value that we're going to need there. Okay, so that's going to be the actual Ka value that we're going to deal with, and I'll put that in a second. Recall that our approximation is valid if that value, so 6.2 times 10 to the minus 8, times 1,000 units, is still smaller than the concentration of the weak acid. And I can assure you that it is, meaning that these values here are negligible, so we can kind of kick those out, and then the consequence is that we can just use 0.1 here and then 0.2 here. Okay, so you can see why I was saying maybe an ICE table wasn't particularly helpful, but it helps to qualify why it is we're going to choose the values that we do in here. Okay, so let's see what we can do to repurpose this expression and actually figure out our problem. Okay, so when we rearrange, we get Ka times, well, actually, let me just put the value in. So let me just make sure I got the right thing there. 6.2 times 10 to minus 8, good. Okay, and that'll be times the H2PO4 value, so that was 0.1. That'll be over 0.2. So notice what I'm doing is I'm rearranging the equation while I'm going through and doing this. I'm not paying attention to the units very much because even though, as far as we're concerned, K values are dimensionless, we are going to need some units at the end here being moles per liter, so we're just going to slam that in here. Now, in my lack of preparation, I've left the calculator away, so give me 2 shakes. Okay, may edit that at some point in the future for content, but let's see how this works out. So 6.2 times 10 to the negative 8 times 0.1 divided by 0.2. Calculator fail again. Okay, 6.2 times 10 to the negative 8 times 0.1 divided by 0.2. Good, okay. So it turns out that our hydronium ion concentration in this solution is 3.1 times 10 to the minus 8. Okay, technically we should have it as moles per liter because that's a typical unit of concentration. And then all we have to do is take the negative log of that to find the pH. Negative log my answer. Looks like 7.51 with correct sig digs. Okay, so a couple of quick things before I wrap up. The first being, notice the interesting thing that would happen if you had the concentrations of both of these concentrations, so the weak acid and its conjugate base, being exactly identical. Okay, if those two underlying values were the same, then the hydronium concentration would be equal to the K value, which is actually great. It would make our job easier, and that's something that we'll talk about when we discuss pH curves. Okay, so kind of watch for that. A little bit of bonus then for you is I'm going to ask as kind of a challenge question, and I think this pops up in one of the labs. If this buffer with a Ka value shown here, okay, so it's a pretty small Ka value, produced a buffer with a pH that was close to neutral, slightly basic, then would it be possible to make a buffer made of different components, so you would not have to use the same chemicals, but one that had a relatively low pH? Well, I think we've proven that that's the case. We did that with an acetic acid buffer with acetate ion. Notice that the pH here is, pretty close to 5. What kind of substance would you have to do then to make a pH that was, let's say, quite a bit more basic, let's say closer to 10? Okay, so I'm going to get you to think about that, and we can discuss at a later time. Thanks very much, and have a good break.